After watching this video lecture, students will be able to explain equilibrium shifts relative to LeChatlier's principle and in the context of temperature, pressure, and concentration changes. So LeChatlier's principle states that if a system that's at equilibrium is disturbed or altered by a change in temperature, pressure, or concentration of one of the components in the reactants or products, the system is going to shift its equilibrium position so that it counteracts this disturbance and reestablishes the equilibrium ratio. That may include, obviously, changes in concentration and affect the overall quantity of your reactants and products at that equilibrium state. So LeChatlier's principle basically allows us to analyze how an equilibrium position is going to shift relative to changes to the system. And in chemical manufacturing or chemical synthesis, we're making specific products. And those products, obviously, if we're making those products from reactants, we want to have the maximum amount of product that we possibly can so that we can maximize our yield and subsequently our profits. So there are several factors that are going to affect our equilibrium shifts. We're going to look at changes in concentration, changes in pressure, and changes in temperature. All three of these can affect equilibrium depending on the reaction system and can subsequently decrease or increase our yields of product. So if we go ahead and we look at this little table over here, notice we have partial pressure, which can be looked at as concentration change, and time. And what we have here is that H2 and N2 have specific quantities at the initial equilibrium, as well as NH3 has a specific quantity. Now we add H2 when the system reaches equilibrium, and what we subsequently see is a shift in the concentrations of all of our components. Okay, so obviously we've added some additional H2, so we have a little bit more H2 present. N2 decreases because it gets used along with the additional H2 to produce NH3. And you notice we have an increase in our product NH3. So by adding additional H2, we have shifted the equilibrium to the right and increased the quantity or the production of NH3. Let's go ahead and look at LeChatlier's principle when we change the concentration of substances involved in the reaction process. Okay, so generically speaking, if we add a component, we're going to shift away from that side of the reaction. And if we remove a component, we're going to shift towards that side. Now, not all components in the reaction are going to affect equilibrium. Only those species that affect K. And the way that we can analyze that is that we can write the equilibrium expression for the reaction before we start answering our questions. Okay, so for this example problem here, let's go ahead and write the equilibrium expression. Okay, so we have our equilibrium expression written here. Okay, notice if I excluded the solids, right? And so basically only the AS4 and CO are going to actually affect our equilibrium shifts. Okay, so let's go ahead and let's talk about the shifts we would expect. So if we add the component CO, as is indicated here in part A, we are going to be adding a component that is involved in the equilibrium expression. Okay, so what's going to happen is as we add CO, the equilibrium is going to shift away from that addition in terms of this equation. So what's going to happen is CO is going to cause equilibrium to shift to the left. Okay, and so we're going to subsequently increase the quantity of our C and AS406. Now, for part B, it indicates that we have removed C or AS4. Now, AS4 and C do not show up in our equilibrium expression. So the addition of these two solids are going to cause no change in shifts. Okay, so we're not going to shift left or right. Everything's just going to remain the same. Okay, and our final example here that we see in C is to remove AS4. AS4 is involved in the equilibrium expression. By removing AS4, our equilibrium is going to shift towards that side, so it's going to move to the right. Okay, and when we shift to the right, that's going to subsequently increase the concentration of our CO. Now, something I want to mention here, guys, is that even though AS4 and C are not involved in the equilibrium position or expression and do not affect shifts, I do want you to understand that they still get used to produce products, or they still get produced depending on the direction of the shift. Okay, so if I do adjust the system so that a shift occurs, if we shift to the right, the AS4 and C6 carbon are going to be used to produce more product, so their quantities will decrease. In that same mindset, if the equilibrium shifts to the left, I am going to technically produce more of these two reactants. So just keep that in mind, that even though they don't affect the equilibrium shift, their quantities can change. Let's go ahead and let's look at LeChatlier's principle with respect to change in pressure. Okay, so some ways to change pressure. First of all, adding or removing gaseous components. So if we add reactant or add product that's in the gaseous state, we're going to have a corresponding shift. Now, this is going to follow the rules that we discussed in the previous slide. So basically, if we add a reactant that is part of the equilibrium expression, we're going to shift right. If we subtract a reactant that's part of the equilibrium expression, we're going to shift to the left, and so on and so forth. With products, the same is going to be true. Now, another option to change the pressure of a system is going to be to add an inert gas. The addition of an inert gas is going to have no effect on your equilibrium position because the gases are not part of the equilibrium expression. N2, argon, those are typically going to be the inert gases that you will end up adding to a system. There are others, and they'll indicate, hey, this is an inert gas. Number 3 is to change the volume. If we change the volume of the container, obviously we're going to alter the pressure of the system. So when we change the volume of the container, when we reduce it, the system is going to reduce its volume by decreasing the number of gaseous particles, and that's obviously to reestablish the pressure equilibrium that was present. Okay, so if we decrease that volume, the shift is going to go towards the side of the reaction with the least number of gaseous molecules. And this could be left or right, depending on the specific reaction being observed. So let's go ahead and look at a couple of examples. So in this situation here, we have gaseous reactants and products. They've told us that if you increase the pressure, which way will the equilibrium shift for the synthesis of ammonia? Okay, so if I increase the pressure of the system by, say, decreasing the volume, we're going to shift to the side with the least number of gaseous particles. Okay, so on this side we have 4 particles of gas. Okay, on this right hand side we have 2 particles of gas. So if I increase the pressure of the system, what's going to happen is the reaction is going to shift towards my products. Why? Because we want to have a reestablishment of the pressure ratio between reactants and products, and that's going to be established by having less overall particles present. Okay, now, so in this context of this problem, they've told us that they reduce the volume. Again, it's going to cause a pressure increase, and we're going to be shifting away from the side with the most gaseous particles. So obviously this side has 6 gaseous particles, this one has 0, so my reaction is going to shift towards the right in order to maintain that equilibrium. Let's go ahead and look at how changing the temperature affects our equilibrium. So in the case of temperature changes, the equilibrium constant can also be altered during the shifts. And we'll talk about that here in a second. So basically, things you have to pay attention to is whether or not your reaction is exo or endothermic. And basically what you're going to do is you're going to treat your heat as a reactant or a product. So if we go ahead and we look at this reaction here, they've told us that it is endothermic. So if we rewrite this equation and write the heat as a reactant, we can then go ahead and analyze how temperature changes will affect this specific reaction. Now that we've written this out, let's go ahead and discuss the addition or removal of additional heat. Okay, so if I increase the temperature of this reaction system, I am increasing the quantity of heat that's being added to the system, and I'm subsequently adding more reactant. If I add more reactant, the reaction is going to shift to the right, decreasing the quantity of N2O4 and increasing the quantity of NO2. If I were to cool this reaction, I'm going to be removing heat, which is a reactant, and basically I'm going to be shifting the other direction. All right, now, Please make sure, guys, that you're paying attention to the reaction type, whether they're endo or exothermic. If it's endothermic, the heat is going to be on the reactant side. If it's exothermic, heat would be on the product side, and then treat the reaction accordingly. So this reaction here gives us a nice visual of what we're going to be analyzing with respect to this endothermic reaction, so these shifts. Okay, so our cobalt water complex here is pink in color, so this reactant is pink, and this product over here, this cobalt chloride complex, is blue. Okay, so depending on the direction of the shift, obviously the predominance of pink color or the predominance of blue color is going to show us what direction this reaction is actually shifting towards. Now, they told us this is an endothermic reaction, so because of that, heat is going to be treated as a reactant on the reactant side. And depending on those changes to heat, that's going to dictate the predominance of the blue or the pink color. Okay, so if I go ahead and I remove heat, okay, so I'm in a cold condition. If I remove heat, this equilibrium is going to shift towards the left, okay? And if it shifts towards the left, we're going to produce more pink product, or sorry, we're going to produce more pink cobalt water complex, and we're subsequently going to have pink color predominant. And this is what we actually see physically when we stick this reaction in a cold system. If we heat up this system, if we increase the temperature of the system, and we subsequently add more heat, the reaction is going to shift towards the right, okay? And that's always going to produce more of this blue product, and you're going to end up with a predominance of blue color, and that's what we see here in the warm condition. Now, at room temperature, when we're at equilibrium, we have both the presence of the pink and the blue, and that gives us a mix of both of the colored reactant and colored product, and we subsequently get this purplish color. Okay, so we can physically see that this shift occurs in this specific reaction relative to how heat is being removed or added to the system through temperature changes. In one of our earlier lectures, we differentiated between the kinetics or the rate of the reaction and equilibrium position. Okay, so equilibrium is established by thermodynamic quantities, while the rate of the establishment of equilibrium is a kinetic property. Okay, and so in the same way we discussed earlier, because catalysts affect activation energy, they affect the rate at which we obtain equilibrium, but they don't actually affect the equilibrium position. Okay, and so catalysts affect the rate of establishment of equilibrium by changing the activation energy, okay, by lowering it. So if we have a lower activation energy, the reaction is going to proceed more quickly, and if it proceeds more quickly, you're subsequently going to reach equilibrium more quickly. However, what I do want you guys to understand or put into the back of your head is that the catalysts, if they're added to reactions, are not going to affect the equilibrium position, only the time it takes to reach equilibrium.